Look around you. Everything you see because of light. It's the universe's ultimate messenger. Light travels faster than anything else we know. It zips through the vast, empty darkness of space at an incredible speed. We call this the speed of light. Imagine a car that could circle the Earth more than 7 times in a single second. That's how fast light is. This isn't just a suggestion. It's a fundamental law of the cosmos. Nothing with mass can ever reach this cosmic speed limit. It's the ultimate speed, the absolute top gear of the universe, setting the pace for everything that happens across space-time. But where does this incredible traveler come from? Light is born deep inside the heart of atoms. Think of an atom as a tiny solar system. It has a nucleus in the center like the sun, and it has electrons orbiting around it like planets. These electrons can only exist in specific orbits or energy levels. When an electron gets a jolt of energy, it jumps to a higher, more energetic orbit, farther from the nucleus. This excited state doesn't last long. The universe prefers things to be in their lowest energy state. So the electron falls back down to its original, more stable orbit. As the electron falls, it has to release that extra energy it absorbed. It doesn't just disappear. Instead, it's converted into a tiny packet of light. We call this packet a photon. This is the fundamental particle of light, a single quantum of electromagnetic energy. Every ray of sunshine, every glimmer from a distant star, every pixel on your screen is made of countless photons. Each one is a tiny burst of energy, released from an atom somewhere in the cosmos. It's a beautiful process, a fundamental dance of matter and energy that illuminates our entire universe, from the smallest firefly to the most massive galaxy. This simple act of an electron changing its energy level is one of the most important processes in the universe. It's how stars shine. Deep inside a star like our sun, nuclear fusion creates immense energy, causing countless atoms to release photons. These photons then begin an epic journey, bouncing around inside the star for thousands of years before finally escaping into space. Some of them travel for 8 minutes to reach Earth, warming our planet and making life possible. Understanding how light is born is understanding the engine of the cosmos itself. It's the key to deciphering the messages written in starlight. Now let's explore one of the strangest ideas in all of science. It's a concept that baffled even the great Albert Einstein. It's called quantum entanglement. Imagine you have 2 photons that are created at the exact same moment and from the same event. These 2 photons can become linked. They are entangled. This means they are connected in a deep, mysterious way, no matter how far apart they travel. They become a single system, even if one photon is on Earth and the other is in the Andromeda galaxy, millions of light years away. What makes this connection so strange? If you measure a property of one entangled photon, you instantly know the same property of its partner. For example, photons have a property called polarization, which you can think of as their orientation, like whether a wave is wiggling up and down or side to side. If you measure one photon and find it has an up and down polarization, you will know in that very instant that its entangled twin has the opposite, side to side polarization. This happens instantly, faster than the speed of light. It's as if the 2 photons are communicating in a way that breaks the cosmic speed limit. This instantaneous connection is what bothered Einstein so much. He famously called it spooky action at a distance. He believed that nothing could travel faster than light, not even information. He thought there must be some hidden information, some hidden variables, that the photons carried with them from the moment they were created. He argued that they weren't communicating at all. They were just revealing a predetermined plan. It was like putting one red glove and one blue glove into 2 separate boxes and sending them to opposite ends of the Earth. When you open one box and see a red glove, you instantly know the other is blue. No spooky action needed. But here's the mind-bending part. Experiment after experiment has proven Einstein wrong. The quantum world is even stranger than he could accept. There are no hidden instructions. The photons don't decide their properties until the moment they are measured. The act of observing one particle genuinely seems to affect its distant partner instantaneously. This isn't science fiction. It's a tested and confirmed reality of the quantum realm. It's a fundamental feature of our universe, a spooky, invisible thread that can connect 2 points in space-time in a way we are only just beginning to understand. For decades, scientists have dreamed of harnessing this spooky connection. The challenge has always been keeping photons entangled over long distances and for long periods. The quantum world is fragile. Any little disturbance from the outside world can break the delicate link between entangled particles, a process called decoherence. It's like trying to whisper a secret across a crowded, noisy room. But recently, a team of brilliant scientists at the Oak Ridge National Laboratory in Tennessee achieved a major breakthrough. They managed to teleport the quantum state of a photon and keep its partner entangled for an incredibly long time. They didn't build a Star Trek transporter. They didn't make matter disappear and reappear somewhere else. Instead, they teleported information. They successfully transferred the quantum properties of one photon onto another, distant photon, using entanglement as the channel. To do this, they used a network of optic fiber cables, the same kind of technology that brings high-speed internet to our homes. These thin strands of glass are perfect for guiding photons along a specific path, protecting them from the noisy outside world and allowing them to travel for many miles without being disturbed. The scientists sent one of their entangled photons on a long journey through this fiber optic network. But sending a photon down a glass fiber isn't a perfectly smooth ride. The journey can jostle the photon's polarization, scrambling the information it carries and threatening to break the entanglement. To solve this, the researchers used a clever system called automatic polarization compensation. You can think of it as a set of smart, tiny hands that constantly and gently nudge the photon back into its correct orientation. This system automatically corrects for any disturbances, keeping the quantum information safe and the entanglement link strong. Because of this ingenious setup, the team achieved something incredible. They maintained the entanglement between their two photons for over 30 hours. This is a monumental leap forward. Before this experiment, keeping photons entangled for more than a few moments was a huge victory. 30 hours is an eternity in the quantum world. This proves that we can build robust systems that can protect delicate quantum states over long distances and for extended periods. This isn't just a laboratory curiosity, it's a crucial step toward building real-world quantum technologies. So why does this matter? What does teleporting the state of a photon across a lab in Tennessee mean for us? The implications are enormous. This breakthrough is a cornerstone for the future of science and technology. First, it opens the door to a new kind of internet, a quantum internet. This wouldn't just be a faster version of what we have today. It would be a fundamentally different and more powerful network. A quantum internet could transmit information that is perfectly secure, because any attempt to eavesdrop on an entangled message would instantly break the entanglement and alert the sender and receiver. This technology could also revolutionize computing. Quantum computers, which also rely on the strange rules of quantum mechanics like entanglement, could solve problems that are impossible for even the most powerful supercomputers of today. They could design new medicines, create new materials, and help us understand the deepest mysteries of the universe, from black holes to the Big Bang. Building a network to connect these quantum computers is a critical next step, and the Tennessee experiment shows us that it's possible. It's a blueprint for the future of information technology. Looking further ahead, into the grand expanse of space and time, the possibilities become even more breathtaking. Imagine a network of telescopes, all connected by quantum entanglement. They could work together as one single planet-sized observatory, giving us images of distant exoplanets with incredible detail. We could see continents, oceans, and maybe even signs of life on worlds orbiting other stars. This technology could be our eyes to the cosmos, showing us our place in the universe in a way we've only dreamed of. It would be the ultimate astronomical tool. And what about communicating across the stars? Sending a message to a future colony on Mars, or to a probe in another star system, takes time because of the cosmic speed limit. But what if we could use entanglement? While it can't send messages faster than light, it could be used to create secure, unjammable communication channels across vast distances. One day, we might have entangled particles stretched across our solar system, or even between galaxies, forming a kind of galactic internet. This is the distant dream, but the journey of 1,000 light years begins with a single step. And that step was just taken, in a lab, with a pair of photons connected by a spooky, invisible thread.